calendar said the Thanksgiving is from 28th to December the 1st. So the next Wednesday, next Tuesday after that
is our last class.
I thought it's December 3rd, but why is it not?
Sorry, what?
So I thought it's December 3rd.
Yeah, so that's, I'm not sure what you're asking, but I'm looking at the calendar again. Yeah, December 3rd, that's, all right, so 26th, so a week from today is our last class period together. The 3rd of December and the 5th of December, that Tuesday and Thursday, we don't have class. That's so that you have that time to work on your projects. So, I mean, you don't have to use that time to work on your projects, but since, it might be helpful to get together as a group if you're already old concept, kind of like all the things that we've studied, it's been around for a while. The basic concept. It's only been recently where people were like, hey, we could use neural networks to do this piece right here, and there was some major advance in solving, and using this to like learn to do really, really amazing and complicated things, like play complicated games with large state spaces, and it leads to like really good demos and things like that. But it's working. Okay, cool. So it's also really it's quite different in many ways in the way it works than what we've been doing. But in the end, there's just there are neural networks and there are optimization, there are loss functions that we optimize, and kind of where those come about in reinforcement learning is what we're going to talk about over the next couple days. And look at some examples of how this has been applied. And the idea is just kind of give you some intro to like, especially today, into like the basics of it and how it works. Maybe go into a few more, like a little more of the more advanced ideas next lecture. But this is really just like an introductory thing. Right? It's 2 class periods, just 1 week. There's a lot more to this topic than we're going to cover. So, anyways, hopefully that's okay with you. Hopefully, I guess I'm hoping that they teach a reinforcement learning course here in the CS department. Does that happen? Does anybody teach that? No, nobody does it here. Okay. Well, maybe one day you'll come back as a faculty member and teach it. All right. So far we've been doing a couple different kinds of like general areas of machine learning. So we spend a lot of time, most of our time in supervised learning, right? When we learn convolutional networks, we mostly were thinking about basic classification problems. At this point, you should have a pretty good handle on what it means to be a supervised learning problem. We're learning a function that takes us from the input to the output. We have spent some time doing unsupervised learning ideas, but not very much. When we were thinking about generative models and learning to estimate densities. So the idea usually here, like the way these problems are set up, is that we have a whole pile of data. This could be thought of like some probability distribution on the configuration of each sample. So these are images. This is like all the pixel values. Like we're in some large dimensional space represented where we're parameterizing all the pixels in an image, and for some of those pixel arrangements, we get things that look like natural scenes, and for other ones we don't. And so you can think of there being some sort of probability distribution kind of describing that, and we're trying to learn that. We're going to learn that structure. And so VAEs and GANs kind of are in this area of unsupervised learning using neural networks. And then, so like I said, today we'll start 2 lectures worth of reinforcement learning, and this is quite different. The setup here is quite different in the sense of like what we really are thinking of now is like we have some sort of agent that can take actions within some sort of space, some sort of environment like state space. And that's not a new idea at all. What's interesting about this problem is that by taking actions, the agent gets rewarded, and this reward is some sort of like signal that's used to reinforce the good behavior, the good actions, and possibly punish the bad behaviors depending on how those rewards are set up. And we're trying to get an agent to act in optimal ways simply by taking actions and getting rewards for those actions. And like I said, this is also, this area has existed for decades. Like the formulation that we're going to go through today has existed for decades. But the introduction of using neural networks to estimate certain parts of this is what is interesting. Okay, so what we'll do today is talk some more about what reinforcement learning is. Reinforcement learning is sort of it's located in the area known as Markov decision processes. So we're going to kind of describe it in that way. We're going to talk about what Q learning is. So this is a way of calculating like how good the actions are being taken. So yeah, and then we're going to actually we're not talking about policy greens today. That shouldn't be on there. Policy greens will come next time. Anyways, we'll talk about Q learning. So yeah, we'll talk about this in a second. But the notion of policy is policy is like is some function for given the state that we're at, taking an action. And so we're looking for these optimal policies, and Q learning is a way of doing that. Okay, so as always, please stop, ask questions as we go here, especially since this will be a very new area compared to where we've been. Okay, so reinforcement learning problems are typically formulated in this way. You think of that as there's an agent who's following some policy and taking actions given the state of the environment it's in. This is like the most kind of abstract way of thinking about this. You can have multiple agents. I suppose you can't really have multiple environments. Like if you have multiple environments, like the whole environment is a union of all the environments that you're in. We'll look at examples of like single agent, multi-agent stuff in a bit. And then the way, like the flow in these things. So if we want to think about like neural networks, we want to think about like how information flows in these models. You start drawing arrows. So the way you can think of this is that the agent. So at time t. But yeah, I should say there's definitely a temporal aspect to this, right? There's like I'm at a current state. The agent's at a current state in the environment. At some time, the agent decides to take an action, and that usually like updates the agent's state. So now, after taking that action, we're at some new state t+1. So anyway, there's this temporal aspect to what we're doing here. There's a sequential aspect here, but this isn't recurrent networks that we're doing here. There's just this idea of like observe the state, take an action, update the state. So just like I was saying, here's a return action. So agent in the state decides to take an action and changes its state. You think of that as like changing the state of the environment. So if like you're playing a game, this is something like you move the pieces around in the game. The state of the environment, in this case the game order, the screen of that if you're playing a video game will be slightly different given the action you take. Or it could be completely different. And then, given that action, there's some reward that the environment sort of like gives back to as a feedback to the agent, saying, this is good, this is bad. So the idea here is, in games it's pretty easy to kind of conceptualize this. There's some, like you get some sort of score. I don't know. You if you do something well, your score might increase. If you do something poorly, your score might decrease. And this is feedback, telling you like what given that state and the action you took, like if that was good or bad. And of course, you can generalize this to thinking about just like any sort of autonomous agent in an environment like yourself. You can think about the rewards given your actions, right? So like, I don't know, you're in this class, you take the action of studying hard, you get an A, that's should be positive, so that like reinforces the behavior that you might get in another time. Or you choose to do something else like skip class, you miss great lectures on reinforcement learning, you never learn it, you miss that job offer, that would have made you a millionaire. You're doing something else really crummy, like making websites. Just kidding. That's the point. And anyway, so this is a very like abstracted way of kind of thinking about how like most of like a lot of interactions happen for us in our own lives and other autonomous agents that you observe throughout the world. So pretty basic. That did the statement. So there's a whole bunch of problems now that reinforcement learning is applied to, and this is like one of the canonical ones. It's this cart pull or like inverted pendulum problem. So the idea is you're trying to balance this pull on top of a cart that moves, right? So there's some point at which the pendulum is attached, so it can rotate on that, and the laws of physics apply here. So gravity is pulling that mass down. So the inverted pendulum, the mass at the top wants to come down. It's like this unstable dynamic system that wants to come back down. But you can move the cart in such a way that it puts this base basically back underneath it, and in some sense keeps the pendulum back up, or puts it back up. But then of course that's created some momentum in the other direction. So now like it wants to fall to the other side, and so now you want to take that cart back. And so there are solutions to this where moving the cart around, you can keep it up, you can keep it from falling down. And so like for whatever reason, this became like one of the very like canonical problems in applying early machine or early reinforcement learning. And think about it in the way that we just described. So what's the agent here? Well, the agent is just someone who's going to have the opportunity to move this cart around on the surface. What's the state of this system? Well, the state of the system is something like, where the cart is, here on this platform. Sometimes this problem is made a little bit harder by having there be a finite platform, and so you also can't fall off the platform. But it doesn't have to be that way. But anyways, so important is just like the angle that this inverted pendulum is making with like this normal vector here, normal to the cart, because that will allow you to calculate things like what should be the angular speed at that point. How will that be changing anyways as you're moving around? And then just anything else, any other forces in this. So there's the force of pulling this down, but then there's also the force of moving this cart. Anyways, you get all this put together. Your actions are you're able to just change the force applied to this cart. So and it's in two directions. So I can change my force to moving us in this direction or in this direction, and again it's a force. So like underneath all this is like basic Newtonian mechanics for like when I change the force, it doesn't mean like all of a sudden like the thing's moving to the left or moving to the right. Like it has to go through a smooth transition of velocity from right to left, whatever. But the point is that this is the universe you're in, and then at each time step you get a reward if the pole is upright, which is typically something like not necessarily exactly upright, but like some small angle with two upright. If you have it there, you get at any time, at some time, you get a reward. That reward somehow needs to be fed back into the system, saying that was a good motion, and or like a good action to take, I mean to say, and then you sort of learn to keep that thing up like that. That was a canonical problem, but like the good news is that we moved way beyond that and have far more interesting problems to apply reinforcement learning to. For instance, this was totally in vogue for a while. I think it's still in vogue, but it's sort of like maybe solved in some sense. But is this idea of like robot locomotion? So you have these models of just different objects, and basically they're just sticks with joints. And so the whole the state of this thing is basically like there's different degrees of freedom for each of these joints, like how what kind of angle it's making with any other joint or with any other stick at the joint, and the composition of all those gives you like some position of this either humanoid figure or this like kind of spider figure, and the action that you can take is basically applying the force to the joints. You can change the angles of these joints, and usually these are put into landscapes where you start at some point, and if you're moving in the direction of the place you're trying to get to, you get rewarded for that. If you're moving away, you don't. But this doesn't know anything about walking or moving or anything like that. All it knows about is like flexing its joints, like changing the angles of its joints, and in that way, it learns to walk. And in fact, I think I have a video on this better. Here the pads. So these are a whole bunch of examples of these kinds of robots learning to go from one position to another. So you can see there's our spider. There was like this kind of humanoid thing, but it only had a torso, didn't have any of the other parts. But in the very first part, you saw like the one with the hands and head. So the point here is that I love these guys. So these things have learned to walk essentially. They've learned to propel themselves forward. So again, there's physics involved here. So every center of gravity of these pieces of the every center of gravity of the pieces of these things is being basically just a gravity is just basic physics is being applied. So gravity plus just all of the motions involved, and it's learning how to walk. It's learning how to walk just by being rewarded to go from one point to the other. Now these are more complicated landscapes, right? They have hurdles to go over, they have gaps to jump over. Yeah, these things, I don't know, additional blocks to go under. This thing has to learn to jump. Look at that. So it's interesting, right? So this thing has learned in this training. Yeah, look at that. I love that. It's like swinging its arm. So these are all forms of walking. They don't look like walking to us necessarily because we walk differently. But nevertheless, they given the world that these things are in, and the rules, just the basic physics that's being applied, doing this thing, rolling the arm or was applying forces essentially on itself that allowed it to propel itself forward.
We want to get at the top.
Yeah. These things would be great in Olympics, right? So anyways, it's super interesting to watch these things learn. And again, I just want to emphasize one more time, there's no programming in here that says here's how you walk. It's simply it's getting rewarded for taking actions. The actions are torques against the angles, which are changing the angles of all the joints here, and doing this literally millions of times. It's learning a way to propel itself from one point to the other. Did you have a question?
So just a quick question, are they given the whole board in front of them, or just have some, the next obstacle in front of them?
No, so basically the whole world's in front of them, and there's a starting point and there's an ending point. And so the reward you get is how is proportional to the distance you move in that, with each action in the direction of the target, the end point. So yeah. So pretty cool. Pretty cool. Atari game. So OpenAI sort of made these like the standard examples now for reinforcement learning. They have this whole thing called the OpenAI Gym, where they provided basically these data sets on like various Atari games. And I know like Atari is a history lesson for most of you, but I did have an Atari when I was like 6, and these were great games. But they're pretty simple now. And this is the reason to use these, is that they're simple. They have very simple rules, very simple states to keep track of, and like very simple actions. But anyways, there's like dozens and dozens of these, and you can go to OpenAI Gym. You can play. You can get the data. You can play with their starter codes for training reinforcement learning algorithms on these things, and you can get something that learns to play whatever Breakout or Space Invaders or whatever. And these are really nice for reinforcement learning as well, because there's already this built-in scoring system for providing the reward to the agent, right? So in any one of these games, from Pong to whatever that last one's on the right, there's already some system that rewards like good behavior. So in Pong, you get a point for passing it across, getting the white pixel there, past your opponent's paddle. And in Breakout, you get points for every time you break out a brick, and I think you get more points for the ones that are higher, and so forth. So really robust reward systems built into this. I think I have an example. Yeah. Oh, here it is. Okay, cool.
Sure, like software engineers get offers from technical.
You too. That's right. Okay, so this is the algorithm that we're going to be learning about today, playing Breakout. And what's fun about this is it shows you what this looks like when you just barely training. So you're going to see something that looks not very good at first. It's going to miss the ball a lot, and stuck in the corner a lot. Sometimes it hits it back, sometimes it doesn't. So at this point, really early on, there's not a really good policy for taking actions given some state here. And again, the state would be the current position of the paddle down below, and the ball, and all the broken bricks. So now it's been training for a while. Now it's getting good. It never lets the ball go past it, and scoring. See, it's getting 1 point, or I don't know how many points for every time it breaks out a brick. Then you let it train for long enough, and it becomes like a super expert. So that's pretty good, right? You can impress all your friends with breakout skills if you could play like that. But now this is taking it to the next level. So it's not only figured out how to score points, but it's also figured out that if it can break through the back, then this thing just bounces around. Every once in a while it has to send it back there. So these things learn. Maybe that's not surprising, that particular example, but they can start to learn really surprising things. We're going to see examples of surprising things in just a second.
So it's a very, very simple game in terms of the rules, but it's a very difficult computation.
Thank you. Okay, so right. So speaking of Go, here's the next one. So a couple of years ago, DeepMind came up with a very complicated reinforcement learning system that was reinforcement learning plus a whole bunch of other components for playing the game Go. I'm not a Go player. I once upon a time learned to play it and played it a few times, but I don't appreciate it like some of you might who played a lot. But this is a very difficult game, not necessarily in the rules of play, but just in becoming an excellent Go player. Like this is a very large board. There's a lot of pieces to it, and the games can be quite long, and there's just a lot of states that the board can be in. So being an expert at this sort of requires you to understand the game very deeply because of the number of states this game can be in. And here's another video. This time the right one. So let's start it.
Okay, so the other side, well, that's why games were invented. There's a rich history of.
So this is Demi Hassabi, I think is how you say his name. He is the founder and current CEO of DeepMind, and a lot of these reinforce, all of the things that a lot of the cool reinforcement learning examples come out of DeepMind. This is what they focus on, thinking that this is the pathway to kind of this. Start talking. So, anyways, this is where they think that the ideas for artificial general intelligence come from. Is these ideas of reinforcement learning.
Another way of doing Go is that
Can you hear this?
the ball is more than the number of atoms in the universe. If you ask a great Go player why they play a particular move, sometimes they'll just tell you it felt right. So one way to think of it is that Go is a much more intuitive game, whereas chess is a much more logic-based game. AlphaGo is our program to actually try and crack Go. We played the European champion Van Ray in a 5-game match. We have an estimate of how strong the program is. Of course, you never know when you play a human player. They do all sorts of very interesting creative things that your program doesn't necessarily do. So there's always an unknown.
When we played the first game, I lose.
I think he was a bit stunned after the first game, and I think he was unsure as to whether he had prepared enough or whether the program was really strong.
I think after the first game, he don't like fight. He like play slowly. So it's why begin the second game, I fight. This is something. I think maybe I'm right. That's why with another game I fight all the time. Now it's but I lose all my game.
AlphaGo won 5-0, which is the first time ever a program has beaten a professional player. The way I see where we are now is that we've beaten the European champion now, and the next step for us is to try and challenge the legendary player Lee Sedol, who you can think of as the Roger Federer of Go. We always used to talk about, well, if we could eventually crack Go and have a program that could beat the world champion, then we must have invented some generic, general purpose algorithm. So maybe we're on the cusp of all of them, and we're very excited about it, but it is just a ladder towards solving artificial intelligence.
Good job, so they went on to play Isidol and beat Lee. It wasn't. Let's see. This happened twice. The first time, I think, Lee actually wants to. I can't actually look this up. I used to know this, but I've forgotten. And I think the second time they got together, Lee didn't win any game. So, what that Lee won just once? Yeah. Okay. So yeah, something like that. So super impressive. The way they did it. So the original AlphaGo algorithm is really complicated. Requires tons and tons of serious compute on the state-of-the-art ASICs for this, TPUs. And there's now other versions of this, AlphaGo Zero was a kind of iteration, and now there's just Alpha Zero. We're not going to get into the details of this, but the point is that the algorithms have gotten a little more general for learning how to play games with these kind of rigorous frameworks. Yeah. Okay.
I have a question.
Yeah.
So the rewards at the very end of the game, Like you want to get zero otherwise. How does that work?
That's a really good question. How does that work? Well, this is a lot like the vanishing gradient problem, right? That we saw like in recurrent networks, where your signal is really far away from the things you need to update. And so, how does this work? So they overcame that in a number of ways. I think we'll talk about some of them. The point is that like you actually train this on like individual transitions of the game. So like this is definitely like a lie of how AlphaGo really worked. You train this on transitions of the game. When you finally get to the zeros, like when DeepMind algorithms have zeros on it, there's a ton of what's known as self-play but you start a game kind of in the middle of like not from the beginning, but somewhere in the middle of the game, so that it's shorter to the ending, and you play that out, the same algorithm against itself, so that that signal does work that way. But this was trained with a lot of like learning how to transition from like some state to another state, and that was rewarded partially if that transition happened in the game that one, or like that move that towards in. So it's actually very complicated. We're not going to get into details of it.
Yeah, so can I say the fundamental difference between reinforcement learning and say other supervised learning is that the reward and movement are just far away, and there's a temporal thing going on here.
Like the real difference here is that like the function that you're trying to learn here is the policy. So the policy, given a state that you're in, is like what action would you take? And the only supervision you get of that is a reward for the action you take. So it's like in some sense it's supervised learning, but it's not because of this notion of you're not trying to learn the reward. You're trying to learn the policy. So like in supervised learning problem, you're trying to learn the label.
Yes.
That's direct supervision. This is like a very indirect kind of supervision where you're learning to take actions, and you only know if that's good by the reward that you get for that. And like the action that you take in a particular state, you might get a reward, but that same action in a different state might not be a reward. It might not be a reward. That could be punished. So it's far more complicated. These things are far more difficult to train. They take way longer. They take way more iterations to train, simply because you're exploring a much larger state space usually. In this combination of state plus action, or state comma action. This is barely came out from DeepMind. This is totally cool. Everybody seen this? Okay, I think this is great. So let me just say before we get started here. So basically, what this is doing, this is a multi-agent reinforcement learning. There's two teams playing hide and seek against each other. There are hiders and there are seekers, and they're put into an environment where there's fixed structures like walls and stuff, and then there's also movable structures that can also be locked into place. And so there's actions like moving. Each agent can move itself, and then it can like move structures and it can lock them in place. And at every step, hiders get a reward of 1 if everybody's hidden, but they get a -1 if anybody's like currently being seen. And then it's vice versa for the other team. They get a -1 if everybody's hidden at a particular action, and then a +1 if anybody's caught. So there are two reinforcement learning algorithms kind of playing against each other, and each one is like changing the state of the system. So this is it's more complicated in that sense, but same basic principles apply. So this is really fun to watch.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The Seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the Seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the Seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent Seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the Seekers discovered that they can jump on top of boxes and serve them to the hider's shelter.
Easter egg.
In the last stage of emergent strategy that we observed, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide-and-seek in parallel for many days. They train against each other, as well as past versions of themselves, using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known today, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.
Sorry, I said this was from DeepMind actually. That came from AI. So pretty cool, huh? What makes this really awesome is visualization, right? So like someone spent the time to like create these awesome visualizations of how that, it certainly wasn't how it was played. Watching these things, I guess you don't want to say visualizations in case you could, but it really brings it home. Like these things have happy faces and sad faces. You anthropomorphize it more and more, and like now you believe the story of like, oh, this is all it will take to get artificial general intelligence. When probably it's not the case. Anyways, so hide and seek. So who knows where this is going next, right? There's like what crazy thing people might learn to do with reinforcement learning. There's tons and tons of other examples here. One I didn't put on here that is an obvious one is self-driving cars, so autonomous vehicles. Like they use reinforcement learning to make decisions about what decisions to make and what action to take given the state of things that they of the car and what they're seeing through the cameras and the lidar and other sensors. And the objective they're trying to attain, like getting to this part of the city. So, anyways, really cool stuff. All right, so let's get into like how this actually works. So now we're all inspired by hide and seek. Let's talk about how this works. So, Markov decision processes. So this is sort of again set in this context. Markov decision processes are really like mathematically just this tuple of 5 different things. You need a set of possible states. So this is like describing the environment or the universe that this is happening in. The set of possible actions. So this is whatever an agent can do in this, or like a video game, go left, right, up, down, jump, whatever. And then the distribution of reward given for a state action. So this is a probability distribution. So given a state in action, you can think of sampling a reward for the state you're in the action taken. So this could be like a deterministic distribution. So like you always get the same reward. Most everything that we saw here was like that. But you could also kind of just generalize this a little bit and say that you can sample from something that, like, where there's some variability in the reward given for any state of action. Given, like, this would encode something about uncertainty about how good that state of action was. The action that you took in the state was. You need some sort of transition probability. So distribution over the next state, given the state action pair. So again, like, this is usually deterministic. Like, if I take, if I'm in a state and I take an action, then I get to this deterministic state. But of course, you can generalize this again and allow that to be, like, the state is sort of, this has some mean change in the state, but that could happen with some sort of variance. And then there's this important idea, the discount factor. And this discount factor is a way of sort of like discounting the contribution of any action in the past to a reward you receive right now. And it's formalized in this way. So at a time step.
What was the last one here? The discount factor?
Yeah, so in this next slide we'll talk a little bit more about it. But let me just say again, like, the idea here is you have all these actions that you're taking that are producing some outcome. So the point is that, like, there's like this history of actions that you're taking, and any one contribution of an action to, like, the current reward is sort of discounted in time. So this gamma, this discount factor, is usually it's a number between 0 and 1, and it's usually, the formulation for this is like the total reward at the current time is it's like this geometric series here where you're taking exponents of so as you move back in time, the reward you received back in time is not as important as, like, the reward you're receiving right now to the overall the overall goodness of the policy. Let me just go through this slide and then ask a question again if things aren't clear, which probably. So at time step, here's how we think about this. At time step t equals 0, so at the beginning, we sample some state, some initial state. So think about the hide and seek game. This is just like where all the agents are, the hiders and the seekers, and all the structures. And then as we go forward in time, so an agent selects its action, this action from this policy. So given the state it's in, we select an action. We then sample a reward for that action given the state that we're in. We then also sample the next state. And again, I'm using sample here because these, like I just described, these things could be probability distributions, but often they're deterministic. And then the agent receives a reward, and then now you're in the next state. So a policy, we usually use pi here as the variable for that, is a function from the state to an action that specifies what action to take in each state. So this is what the agent is using to select its action given the state. And what we're trying to do is we're trying to maximize. We're trying to find a policy. So some policy that maximizes this discounted reward. So again, the idea here is actually, it's funny how that's said there. That should actually be. It's sort of reverse here. But anyways, like if I'm in, so the way that this should be right here is like whatever time I'm at, that's like whatever my current time is right now, that's the thing I should be getting exponent of 0. And then because like that's the reward I'm getting at this current time, and then the reward I got in the previous time step is multiplied by gamma, which is between 0 and 1. So whatever the reward was, it's smaller now. And then if I go back 2 time steps, it's multiplied by gamma squared, which is even smaller still. And And so what we're trying to do is we're trying to maximize this cumulative reward over like our whole sample in this space. Okay, so cumulative discounted reward. So like simple examples, how does this work? Here's our states that we can be in. So we have an agent that can be in any one of these states, any one of these boxes. It's trying to get to the start boxes. So the idea is every time that you have to take a transition, like that means that you're not one of these states, we're going to reward you with a -1. So maximizing that cumulative discounted reward is the same as like trying to make as few transitions as possible, right? Because every time you make a transition, you're going to subtract something off of it. You're going to make it smaller. We're trying to maximize it. So what are our actions in this? We can just, if we're in any state, any cell in that grid, we can go any direction. So again, like the objective is to reach one of the terminal states in the least number of actions. So if we're just sort of, if we're just sort of, if we set our policy just sort of randomly chooses whatever direction, just any one of the directions sort of uniformly, then this is what our world looks like. Like this is what our policy looks like. We just go anywhere. But an optimal policy will do the obvious thing, which is wherever I'm at, I'm gonna move in a direction that will like sort of traces like the shortest path to a nearby like starred cell, right? So if I'm right next to it, there's only one action that my policy should tell me to do, and that is move in the direction of the starting cell. And if I'm not right next to it, then I want to move myself in that direction and so forth. And so this is like this is an optimal policy, meaning it would have the given any starting state, this would have the maximum discounted reward, cumulative discounted reward. Okay. All right. So it's optimal policy pi star. So we want to find this optimal policy, and so maximize the cumulative discounted reward. And so how do we handle the randomness involved in sampling? There's like sampling the initial state, sampling the transition, sampling the new state in the environment. If it's deterministic, this is pretty simple. But if not, what we do is we just take expectations. So and again, this is again like the general way of kind of presenting these ideas, where there are distributions everywhere. So again, this is the thing that we're trying to maximize. So we're trying to find a policy. So pi star is the policy that maximizes this this thing, but we now think of it as like the expected cumulative discounted reward, where the expectations are taken over these different distributions, and yeah, so we have this, our initial state drawn from this distribution, our actions drawn from this distribution, so the policy being a distribution from the state, and then our state our new state is drawn from this distribution. So we're basically we're integrating over all of those distributions, and marginalizing them out, so all we have left is the expected reward. Yep. Questions about that? If it's deterministic, then it's only ever picking one thing anyway, so there's really nothing to integrate out. But if there's some, if it's not that way, then we integrate. Did you expect this kind of hard? Yeah.
And so I'm thinking, so suppose the gamma discount rate is between 0 and 1. That means the initial state, initial movement contributes least to the objective. And that means, maybe for some games, your initial movement is much more important, way more important than your later movement. So, how does that get into these situations?
Yeah. So, it's still there. It's not like it's not there. Notice that one thing that this is doing, there's an implicit preference for policies that maximize the reward, that obtain their objective in a shorter amount of time, right? Because then these better decisions, the discount factor on them is not as small as they would be on very long, policies. Again, the point here is just to emphasize that all the decisions made contribute, but they contribute different just given when they happen in time.
So I'm thinking, so when did it take the discount? So do they assume that we are at the beginning of the game and we discount all the future reward back to now, or we are at the end of it and then we discount all the previous?
Yeah. So the policy basically gives you that thing is over the entire.
Discount all the.
You can think of it as multiple trajectories. That one policy is going to trace out. That's what the expectation is about. It's tracing out multiple trajectories through the game.
Yes.
And if it's deterministic, you're basically going to trace out the same trajectory every time. But with the randomness, you might take a lot of different paths, right? So this maximization happens over all those paths. And it's and so the ones the paths that through the game that show up a lot are the ones that contribute most to that expectation. Does that make sense? Maybe not. Okay. Keep asking questions if it doesn't, but yeah. So keep thinking about that and asking more questions. I'm going to keep going through this because we're starting to run out of time. But I need to get a couple more ideas from Markov decision processes out here, because this is where the neural networks are going to start to come in. So there's a couple of auxiliary functions that are going to help us evaluate how good things are. So given a policy, we can ask how good is any state in the environment. So the way that we do that is we compute, again, here's our discounted cumulative discounted reward. We compute the expectation over this, but this time, this is always just given the policy. But this time, we're given an initial state S. So the way that you think about, one way of thinking about how good this state is by asking what are the expected cumulative rewards if we start, given this policy, if we start in that state. Okay? So if these are being really, really low, this would be a bad state, but if we start here and they're really high, this is a good state, right? So this is a pretty reasonable way of evaluating how good a state is. And this is called the value function. We use the letter V for that. And then we might ask a similar question, which is, how good is a state and action pair? So this is called the Q value function, or just the Q function often. And again, it's a function of both the state and an action. And it's, again, really similar to what we had before. It's just we now say that action is the initial action. So we sort of talk about the value of so given a policy, the value of this state-action pair is the expected trajectory if we start in that state and take that as initial action. Okay? And again, once we do that, then the policy kind of takes over and determines, whatever actions we take next, and then that changes the state and so forth. And so again, these expectations are taken over the future states and actions that we get to because of the policy. The value function and the Q value function. Actually, I have no idea why it's called Q value. Probably some good answer to that, though. Q value. So anyways, these are just ideas from Markov decision processes. All right. Questions about that? I'm just throwing out definitions here. They sort of seem reasonable, right? how do you say how useful or how good something is? Let's start with these things and see what our cumulative reward ends up being. Okay. All right. So this is where the rubber hits the road. We have the Bellman equation. So for our Q value function, an optimal Q value function is the maximum. So given that state in action, yeah. So an optimal Q value function. So remember that these are functions over, like, in this case for the Q function, over the entire, like, state, state times action space. So an optimal one is one that from a given state action pair, the value you get here is the max over all of the possible policies. So it's the same expectation taken over here, but not just given a policy, it's over all the policies. So this is like, so for this state action pair, this is like the maximum value we can get for any of the policies that we could possibly use, that our agent could possibly use. All right, so that's what it means to be an optimal Q value function. And what's interesting is that this this optimal Q value function actually satisfies what's known as the Bellman equation. And this is a really interesting, like, what's the right word?
Recursive?
Yeah, recursive, thank you. I kept saying recurrent in my mind, that's not it? Thank you. Recursive equation. So you can define so for any state and action pair, you can define, or like the optimal Q value function is defined in this way. So I have, let's break this apart. So I have an expectation over all of my possible states, and what I have is this. I have this discounting factor coming in here. So this is like taking a step. So this is like, okay. This is like the previous action that I took, or like this is the previous state and the previous action that I took. And then that got me to some new place. I discount that value, and I add to that the reward that corresponds with the current state in action. So when I take an expectation over that, so an expectation over all the states, all these other states, and then I maximize that with respect to the actions, I actually get back the optimal state action, or the optimal Q value function. So reading what I have written here, if the optimal state action values for the next time step are known, then the optimal strategy is to take the action that maximizes the expected value of that.
Excuse me.
Yeah.
I think the S and A are the current state and action, and S prime and A prime are the next step here.
Yeah, that actually might be right. Hold on. It's certainly the way I have it written down there. So it's different from what I just said. So hold on a second. Yeah, somehow that seems wrong, even though this would be contradicting what's written there. And I can't resolve it looking at it right now.
think it's right. The S prime and H prime are the all. So S prime are all the future possible states. We just.
But are you saying that for a different reason than just the fact that I've got it written there?
Which one?
Just that I have it written right here. Are you saying for a different reason, like you have?
Yeah, next.
What are you saying, like, given the current state, maximize the future state? How do you don't have the future state necessarily in the current state?
Actually, what I'm confused about is the way the discount factor is being applied.
So discount, I think they discount all the rewards to the beginning of the game. Right? So, for example, P equals to 0, that means the first reward has the largest contribution.
So the gamma to 0, right?
Yeah.
Yeah.
But you said it's the same thing, because you're just maximizing your expectation over 2 states.
Yeah, I don't know. I can't resolve it. I'm telling it to you, kind of formulated in one way, and now, but I haven't presented it and formulated it any other way. And so now I'm really confused. But you should be able to resolve it like this. So let's see. So when you apply the discount factor to the future, oh yeah, right. Yeah, it is formulated. Okay, got it. So that's okay. All right. So I'm gonna think about this some more, so we can get through some of the other slides, and I'll have to come back next time and clarify it. But yeah, so this is discounting future states. Yeah. So like all this is formulated in like the complete opposite way that I've been talking about it.
Because
You're discounting future states. That's right. Okay. That's right. You can actually formulate it both ways, but I guess you just do like.
So you talk, were you getting the learning rate? There's another value called the learning rate. It's applying to the current value.
No, not the learning rate. I mean, the learning rate is what we use when we like have neural here, which will appear just a second. But yeah, so we're discounting future states, their contributions that we would take. That's right. Okay. So, right. All right. So like 3 slides ago, I said something like the following. Let me go back. How many slides ago? Yeah, about this being like this being not right, but it actually is right for this formulation. So the way this is formulated is that we're discounting like future states. So like future rewards that we could take. So they come, yeah. So as we move forward in time, so like wherever we are right now, yeah. So okay, good. Sorry, wish I would have gotten that worked out first. So when we look at these things here, when we're doing these expectations, what we're saying is something like these are all the paths that we can take from the current state and given actions, and there's like a lot of different ways we could go into the future, and the further away the reward is from us from us like currently into the future is we discount that more and more and more so that it doesn't influence as much the current reward that we're receiving for this. Yeah. Sorry about that. Okay, right. So when it's set up that way, then you come back over here to these definitions. And here, this is pretty sort of easy to I don't know if it's easy, but like the intuition is a little bit easier to understand. And that is we took a current state in action and we got a reward for that. And now what we want to do is we want to maximize this this function, which is just this cumulative sum over all of our policies with respect to whatever action we can take next, which will give us the updated state. And that, because it's in the future, is discounted by a factor of gamma. And then we just take expectations over all the states we could be in, and this actually gives us the value of, like the optimal value of the Q function at that state in action. So it's like taking one step. So like this term right here is like taking one step forward in time, like in this. So it'd be like R. This is like R0, and then this is something like the R1. This encapsulates all of the like a future value, like optimal future value coming from our Q value function. And so anyways, let's see. Yeah, that's right. And it's discounted by that single factor because it's like you've taken one step forward. So this equation right here holds for the optimal Q value function. Yeah, so again, reading this, and then hopefully this won't feel confusing now. If the optimal state action values for the next time step, Q star, are known, then the optimal strategy is to take the action that maximizes the expected value of this. So again, this is like in some sense, like encapsulating all the future value in Q. Okay, we're not proving that, we're just stating it. And what happens now, and now that you have this recursive formula, you can actually use this to find the actual Q star. So this is like something like what's the term? Anyways, so notice here what we have is we have a Qi and a Qi plus 1. So if we can compute all the things in here, then we can continue just to iterate this process on the Q value function. And as this I gets large, then this function is converging to our optimal Q value function. And what's important about that? Oh yeah, I don't know if I ever. Well. So what's important about that? So going back to this. What these Q values, these optimal Q values are going to do for us is to help us define like the optimal policies. So remember that the Q, I didn't say this when we went to the next slide, but the Q star, so the optimal policy pi star corresponds to taking the best action in any state as specified by the Q star. So our optimal Q value function actually is a thing that will help us to find the optimal policy. We can just like given any state of action that we're in, we can think about like all the transitions we can make, and just take the one that maximizes that, and given all the possible actions we can take in the transitions we can make, and take that action, and that would actually be an optimal policy. So it's to our advantage to be able to compute this thing. It's a pretty complicated thing. Like here we're saying we can iterate towards it, given the recursive function, or the recursive relationship here. But the problem is that this thing just obviously doesn't scale. So like computing this thing for every state action pair could be horrific, right? Like the state space could be huge, the action space could be huge, the product of that would be even bigger. Right, so this could be like this is not maybe like something we can just kind of brute force our way through. Yeah, so like this is a good example of the game state is in terms of pixels. There's going to be a huge number of arrangements of those, so we just can't go and search through it. So this is one of the things we've run into in the past, where like when we were doing VAEs, we had this probability density that we wanted to be able to calculate, but like we couldn't just calculate the integrals involved. So instead of just like thinking in that way, what we do is we learn a neural network that is just this function. So we're going to learn, we're going to learn a function, a Q function that's parameterized by a neural network. And it works like the following. So we're going to, so this function will take a state and an action as input, and it's a neural network, so it's got a bunch of parameters, theta. And what we're going to hope to do is we're going to hope that this learns to, we're going to train it so that it learns to be the optimal Q value function. So so when this is a deep network, this is where the name deep Q learning comes from. And these are our weights. So the way that this works is if we take this Bellman equation and we think of it as something that we're going to iterate towards, our loss function is going to just be like an L2 loss, right? So we have like some target that we want to be at, and the current, just the current output of our neural network. We square it out. We want to minimize it. What's the output? The output is this thing right here. This expectation over this term and maximizing it over the over all the possible actions. And how do we do that? So what is it? So first, what does our backward pass look like? So this is what the gradient update looks like. You have so taking gradients with respect to the weights, these are the things that need to be adjusted. We have our expectations, not only over the state space, but also over over our actions that we could take given the state that we're in. And then here's like the iterative piece, right? So there was this idea of Q. So this is Q at position I, and here's Q at position I minus 1. So these are now, think of these as like every time we update the weights, we're getting like a new version of Q. So what we're trying to do is we're trying to make our version of Q like this version of Q right here, or like this this optimal. This is coming from the Bellman equation, which I don't have up on the board right now. And then you have this product rule, so times the gradient of the network with respect to those parameters. So these are so this is the thing right here that's trying to make the new update like the Bellman update, times this gradient. And so so this is how we're going to supervise. So this is how it's supervised. This is what our backward pass looks like. So this is how we're going to update the parameters of our network, and we're gonna just draw mini batches and estimate all those expectations and hope that this works. This is what I'm saying. We're just really trying to get the Q values to be close to the optimal values as given by the Bellman equation. So how does this work in a particular case of a simple game like Atari? So your current state. So one way of approaching this is to take in breakout. I guess it's 84 by 84 pixels, and that would be RGB. I guess if the colors matter, but my guess is that the colors don't matter. And then in this formulation, you might take the current state, the current state of the game, and then the three previous ones. So there's 4 frames, the last 4 frames. Oh, here it is there. RGB, go to grayscale because we don't care about. Oh yeah, and downsampling properly. Anyways, so you take the original pictures and then you compress it a bit, and then you start doing convolutional networks. And here you see actually a really simple convolutional network. So you stride. So you have an 8x8 convolution filter. You stride by 4. You have 16 of those channels, and you do this again with 4x4 convolution, stride by 2. You have 32 of those filters. And then you go to a fully connected 256, and then a fully connected layer of 4. And the reason why you have 4 is because there's 4 actions you could take. So I guess the reason for the 4 here is something like left, right, up, down. Although I guess in a game of breakout there really is only 3 actions, right? Left, right, and not don't move, no action. But the point is that this is now, you have some layer that's giving you, that's producing the Q values for the different actions. So given the state, we get our Q values for these different actions. And then the optimal is going to pick up the largest Q value. Right, so given this state, the 4 different actions you could take on, I think a breakout is probably 3. Yeah, so it's saying the number of actions you could take just depends on the game. Yeah, so the point of all this is like, if this works, if you can get this thing to converge to something that resembles the actual like optimal Q value function, then to make a decision on what action to take, you only have to just do a forward pass to this fairly simple neural network. And that would actually be really, really fast compared to like all the other like expectation things you would need to do, searching the whole space, given like the formulation of Bellman. So yeah, I think it was the last slide. Oh, okay. So these are all the pieces coming back there again. All right. So there's a couple minutes left, and I'll come back to this at the beginning of next time. But I just want to stop and ask for questions. Yeah.
How does the neural network take the action A as the input?
It doesn't take the action A as the input. It's generating the values for each of the actions it could take. Yeah. So I'm trying to think if there's actually a fourth thing in breakout, but you can just go like left, like the paddle was like turn right, turn left, or like don't turn at all. So there'd be actually 3 for breakout, and so there'd be 3 values there. So here's your state at whatever time you're at, and then it's going to give you 3 values for the Q function, and one of those is going to be maximal. So that's a lot like like having something like a softmax or something at the end, where you do an arg max for the optimal action.
And so, could you go back to the previous slide?
Yeah.
Or
this
the equation, yes. Yeah. So here, y, I think we already assumed that the computation of yi is infeasible because we have so many possible future pairs. Then how could we compute y here?
Yeah, so what you do is you do this over mini batches. So these expectations are then estimated by like simple averages over the mini batch. Does that make sense? So like it's a pretty like severe estimate, or like severe is not maybe the wrong word. Like it could be a pretty bad estimate of that expectation, but this has always been the case for like all of the all of the mini batches have all the stochastic gradient descent that we've done could have suffered from this as well. That we're estimating the actual gradient by some some noisy estimate, just meaning like some simple average over a small number of samples. So the same thing applies here, but again, like magically, in gradient land, this tends to actually work just fine.
But I think even for a mini batch, the number of possible state action pairs also is very large. Remain the same.
So typically, like the number of actions is going to be small compared to the amount of things in the state, and then your mini batch is going to be made up out of like, just like a few numbers of those states. So the product, like there's still a product there, maybe that's what you're getting at, but it's much smaller. You're not searching the whole space for every single one of these gradient updates, just for the one, just for the thing in the mini batch.
So be confused, like, is it mini batch, is each record a step? Is each record a new state? Like, what is like?
Yeah. So for training a Q function, each one is like it's a different state.
Okay.
It's a different state. So like in this case, this would be like these things right here. So like a mini batch would be made up out of those things.
Okay.
and then you'd be predicting the Q values for each one. And you'd have, that would be supervised by, the actual rewards coming, so the actual rewards coming out. So like, there's a whole bunch of these expectations to do all along the way to get at these values, but you just use what you have in there. So again, like notice that like the expectations are taken over, these over the state space. So like again, like you're just using a mini batch on the state space to estimate that expectation. And you're doing it just for the gradients. So, same things apply. Like they're actually having a bit of a noisy gradient actually acts as a regularization for the training. So you actually get a more generalized. So just in the same way that like, stochastic gradient descent, like when we were talking in the convolutional network. When we're talking about convolutional networks. So, it could be thought of that like the fact that we don't actually have the real gradient, we just like the actual gradient of like the entire loss function, we just have it for that mini batch. You might think of that as like a problem because it's maybe a really poor estimate of the actual gradient. It turns out that like the fact that there is some noise in there means that you actually kind of like take more of a random walk in the loss space, like on the loss surface, and that tends to actually have a regularizing effect, so that you don't, you have like there's more of this ability to explore, and therefore like find possibly better, like you have the opportunity to kind of move out of like local limit or advantageous, or it's just like it just gives you like more of a random walk, so that you're exploring more of the space, and it tends to lead to like more generalized, like a better generalized solutions. Yeah.
So the neural network you are using here takes in the state and outputs the action, right? So yeah, but that seems to me like a policy function, not a function.
Yeah. So it's the way I know what you're saying, but the way to think of it is that the thing that's coming out here is the value of the function at the state. The value of the function Q, the Q function, at the state and the action, right? So like just think of it like this. Each one of these, so you're basically getting 4 values of the Q function, all at the same state, the input to the network, but for each of the different actions that you could take. Yeah. Other questions?
Yeah. So with that, so basically that one like Q state 1 action, basically saying like you do that action, then you have a new set of actions that are available for you. Calculate the weighted, like weight that lower, and then calculate that, and then you keep on doing that. Is that correct? Right, where you're basically like traversing down a.
So I'm not sure if I understood. So let me just say it this way: what you're doing here through this process at every iteration is that you're learning the Q function, like the optimal Q function. So the fact that it's being supervised this way means that like the neural network is converging to the optimal Q function. Once you have that, then you can use that to have access to the optimal policy.
Right. I guess, and maybe my question is like how like the Q function itself is saying like, give me the state now plus the next state with discount that plus the next state after that and discount that, and then sum all those. Is that correct? Is that the Q function?
You mean like how was it originally defined?
Right. Like
yeah. So
that's how I understood it, right? Is that you're basically saying like discount the next step, and then discount the next step after that, and discount the next step after that.
Yeah. So that's right. So this is like given the policy.
Right.
Just Q without the star. Given the policy, this is the expected cumulative reward if you start in that state with that action.
Right. So isn't there like a potentially infinite number of steps after this?
Yeah.
Maybe like truncate T at some point? Or how does that work?
But notice that like there's no t in any of the things that we're doing because of the Bellman equation. We just have a recursive equation that like captures all the future t's here. Does that make sense?
Yeah.
Okay. And so we get all that like implicitly.
Gotcha.
Okay.
So in the loss function, the expectation still is over all the state action pairs, still many state action pairs. So how?
Yeah.
That's the same application, I think.
Well, you're just saying like this part of the expectation. So like there's this one right here that's like the mini batch, and you're saying like this expectation right here. Is that what you're saying?
Yes, that doesn't seem to same computation.
Well, so the way to think about that is just that like your batch is giving you like a whole bunch of these Q values, both for like your old network and for the new network. You're just filling in these values. So I don't know. When you sample, you just like it's always over all the actions, but the states are limited to the ones in the mini batch. And then you're just filling in, you're just filling in those you're just taking averages, everywhere you see this, you're just taking averages to the things you have access to. Okay, we're way over, so if you have more questions, come up and ask me, and then we'll do the second half of this where we do like a little more sophisticated things, the reinforced algorithm.